Okay, so here finally we return to the IV analysis of the voltage regulator using the Zener diode, and this is the sort of analysis that we started doing in class. So notice we're connecting the two circuits, and we will be looking at the intersection on IV graph. Alright, and notice that we'll be concerned with this positive VI or V Thevenin, you can think of it. And so this circuit, notice the polarity, and you can probably convince yourself that in the IV characteristics, this positive current will flow when this voltage is positive, and for this definition of this of the circuit here, okay, current flows out of its plus terminal. Okay, it's going to be in this first quadrant, some sort of a line. Okay, and in this first quadrant of the IV curve, shouldn't be I. Maybe I'll just use first. That's the first quadrant, mathematically speaking. This is going to be a source. All right. Okay. In this case, the Zener diode here. Notice the current flows into the way we defined it here, flows into its positive terminal. Okay, do it like this. All right, and in the first quadrant, this Zener diode is going to be a load, and we know it's going to look kind of like a regular diode, but this is going to be its VZ breakdown. Okay, and so where these two curves intersect, that's the operating point. Okay, notice that this V Zener is only supported for this positive current, right? And if we look at all the possible lines like this, okay, the diagonal lines that represent the source on the left, some of them will intersect the vertical part of the Zener diode curve, like this one, okay? But some of them at some point can represent, intersect this horizontal part of the curve, which represents the Zener diode that's in the off state. All right, so what is the slope of this line going to be guided by? Well, it's going to be guided by some sort of resistance relationships, right? Okay, so RL and RI. Okay, so we'll see at which point the curve intersects on the off part, and at which point the curve intersects in the breakdown part. And let's give ourselves a little bit of room. Okay, so let's redraw this IV curve, I, V, and we mostly concern ourselves with this first quadrant in this situation. And again, remember that because of the way we defined the polarity of the current and the voltage for the two different circuits, this circuit will be the load, as in it will sink energy, and this will be the source. Okay? All right. So the Zener characteristic is pretty easy, I guess. You can convince yourself that for this polarity of how we defined I and V, we're looking in the first quadrant at the breakdown region, and so it's gonna current is gonna stay zero until we reach VZ, and then any current, at least mathematically, any current can flow through it. still at that VZ. All right, that's of course a mathematical approximation. If you put enough current through anything, things will burn up. But let's just look at it this way. All right, so the slightly harder part is to look at that circuit on the left and draw its IV characteristics. But that we've done a lot before the first hour exam. All right, so we can look at it. We know it's a line, and so we need to find a couple of intercepts, right? So let's look at the intercept when voltage is 0. What does that mean? When the voltage is 0, this is going to be I short circuit. Okay, because it's the short circuit that will ensure that this voltage here, this voltage is 0. Okay, so we can imagine connecting the short circuit here, and that's going to be our I intercept. Okay, so none of the current is going to go through the load when we connect the short circuit, because the load resistance will be shorted out, right? And the current is then just going to be here, VI divided by RI. All right, so this intercept point is going to move higher when we increase input voltage, right? And when we decrease input resistance. All right, let's find the other intercept, and let's, for the sake of argument, put it right here to the right of VZ. Okay, and that's our circuit. And this point is our open circuit voltage. All right, so if we don't connect anything to the output and just look at the open circuit, then we just have a simple voltage divider rule. Okay, and we have V open equals V in times R load divided by R in plus R load. Okay, if you cannot write an equation like this right away, if you have to use Kirchhoff laws, then you haven't yet learned enough about something like a voltage divider. You should be able to write this right away just by looking at the circuit. Okay, all right. So that's what this is. Right, this is V in times RL RI plus RL. All right, and as you notice, when you increase resistance, when you increase load resistance, it will move to the right. When you decrease, this point will move to the left. Okay, so when RL is small enough. And of course, the critical point is right here. And if you solve for which RL brings us, bring this V open circuit to V zener, okay, if you solve for that, then you have your condition for RL that you've previously derived. Okay, so we can draw these three lines, and we can also mark this direction as RL goes down. Okay, so think about it. What this tells you graphically is load resistance goes down, the slope of this line increases, right? Because it's moving the intercept with decreasing resistance, right? The slope, well, the negative slope increases, and the controllability of the voltage across that load at some point reaches a critical point, and past that point you can't control it. Okay, so that's the third way using IV analysis to look at the voltage regulator. And the benefit here was that we looked at this I short circuit and V open. This is of course also how you can find the Thevenin equivalent of any circuit, and essentially we did. You can continue and find the Thevenin equivalent of this whole circuit. Okay, and already V open is essentially V Thevenin of this whole circuit. That's what you just did. You found the Thevenin equivalence. V Thevenin is V open. Okay, and R Thevenin is V open divided by I short. Okay, so some review of this as well. Okay, so practice it. See it in all three ways, and I think you'll find that you know everything you need to know about the voltage regulator. Okay, thanks for sticking with it.